When we describe a loudspeaker, we often use subjective words. We might call it neutral, transparent, bright, harsh, musical, or detailed. Those descriptions are useful when we talk about what we hear, but they do not tell a designer how to select a driver, build a crossover, or change the shape of a cabinet. For that work, we need measurements that are objective, repeatable, and connected to what listeners actually prefer. So the question is not whether listening or measuring is more important. The real question is, which measurements give us the most useful picture of a loudspeaker's sound? D'Appolito identifies a group of measurements that, interpreted together, provide a strong basis for predicting loudspeaker preference. The full list includes frequency response, impulse response, cumulative spectral decay, polar response, step response, impedance, sensitivity, distortion, and dynamics. This first part concentrates on 4 connected topics: frequency response, cumulative spectral decay, the periodical CSD, and diffraction responses. Together, they show not only how much sound a loudspeaker produces at each frequency, but also how that sound changes with time and listening angle. This is a frequency response measurement. Of all the individual measurements, frequency response has one of the strongest relationships with listener preference. In general, preferred loudspeakers have an on-axis response that is smooth and close to flat, but the on-axis curve is only one part of the story. The listening window response averages several positions across the normal seating area. It should remain similar to the on-axis response, apart from a gentle roll-off at the highest frequencies. Early reflections describe the first strong sounds returning from nearby room boundaries. Sound power represents the speaker's total output in every direction. In a well-behaved design, these curves change smoothly rather than showing abrupt peaks and dips. This is an impulse response measurement. It is the time domain measurement used here to derive a reflection-free frequency response. The ideal frequency response measurement is made in an anechoic chamber, where reflections are absorbed and the microphone receives only the loudspeaker's direct sound. Most designers do not have access to a chamber, so a practical measurement begins with the impulse response. In this example, the direct sound reaches the microphone at about 3 milliseconds. The first major reflection arrives a little after 8 milliseconds, after bouncing from the floor. By placing a time window between those two events, we keep the loudspeaker's direct response and exclude the later reflection. The selected part of the impulse response is converted from the time domain into the frequency domain with a fast Fourier transform. The result is called a quasi-anechoic response. It is not a true chamber measurement, but within its valid frequency range it removes the room's early reflections and gives us a close view of the loudspeaker itself. This technique makes useful free-field measurements possible in an ordinary room, provided that the speaker and microphone are positioned carefully and the time window is interpreted correctly. Time windowing has an important limitation. Here, the reflection-free interval is only 5 milliseconds long. A 5 millisecond period corresponds to a frequency of 200 Hz. That means the falling curve below 200 Hz is not reliable loudspeaker data. It is a consequence of the short analysis window. The same window also limits frequency resolution to roughly 200 Hz, so narrow details may be hidden. A clean-looking curve is useful only when we understand the limits behind it. To recover the bass response, we use a near-field technique. The microphone is placed very close to the woofer to measure its output, and then near the port to measure the port contribution. Those signals are combined with the correct amplitude and phase weighting. The resulting low-frequency curve is then joined to the quasi-anechoic curve, in this example at about 300 Hz. The completed trace combines two different measurement methods, each used where it is most valid. This is still frequency response interpretation, not a step response measurement. Step response is listed among the full measurement set, but it is not analyzed in this Part 1 article. Broad changes in frequency response often have recognizable subjective effects. A raised bass region can make a loudspeaker sound boomy or muddy. A rising treble can make it sound bright or unusually detailed, adding extra sparkle to cymbals and a harder edge to brass instruments. If the rise is excessive, many sounds can acquire the same artificial sizzle. A broad depression through the mid-range can make the presentation seem dark, with voices and images pushed farther away. These descriptions are subjective, but the response curve helps us identify a possible physical cause. A resonance can be described by its center frequency, and its Q-high Q resonances are narrow, while low Q resonances spread across a wider frequency range. The detection thresholds shown here reveal an important pattern. A very narrow resonance may need to rise by roughly 10 decibels before it is obvious in typical program material. A broad resonance can become audible when it is only 1 or 2 decibels above the surrounding level. This is fortunate for short window measurements. Limited resolution may hide a narrow peak, but broader and often more audible errors remain easier to see. A conventional frequency response graph shows level versus frequency, but it does not show how quickly the sound stops. Cumulative spectral decay, or CSD, adds a time dimension. Frequency runs from left to right, level runs vertically, and the successive slices show the response at later moments. Ideally, the energy would disappear immediately after the input stops. Real drivers and enclosures store some energy, so parts of the response continue to ring. On a CSD plot, that ringing appears as a ridge extending along the time axis. In this example, frequencies above 5 kHz decay by about 20 decibels in less than 1 millisecond, and there are no major persistent ridges. The low frequency area appears to decay much more slowly, but this must be interpreted with caution. As the calculation moves later in time, the remaining analysis window becomes shorter, near 4 milliseconds. Only about 1 millisecond of data remains, giving a frequency resolution of roughly 1 kHz. Much of the apparent low frequency tail is therefore a processing artifact rather than reliable decay information. Now compare that result with a small two-way loudspeaker used for public address announcements. Its on-axis response is highly irregular, with large peaks and dips across the band. The CSD plot shows ridges at many of the same frequencies, revealing energy that continues after the original signal. A peak in frequency response tells us where the output is excessive. A ridge in the decay plot tells us that the system is also storing energy there. Together, the two views make the resonant behavior much easier to identify. This metal cone mid-bass driver provides a more detailed example. Its frequency response contains strong peaks near 6, 8, and 10 kHz. The decay plot shows ridges at those same frequencies. The 6 kHz resonance takes about 3.2 milliseconds to fall by 30 decibels. The CSD also exposes delayed resonances around 1, 1.5, and 2 kHz. Those features are not obvious in the first frequency response curve because they develop later in time. A resonant driver is not automatically unusable. In the design described by the article, this metal cone was used successfully as the mid-range in a three-way loudspeaker. Its upper operating limit was kept near 2.5 kHz, and a steep crossover suppressed the severe behavior above that frequency. The lesson is practical. Measurements do not merely classify a component as good or bad, they reveal the range in which that component can be used safely. Ordinary CSD is based on elapsed time, and this creates a disadvantage at low frequencies. A high-frequency resonance completes many cycles in a short interval, while a low-frequency resonance needs much more time to complete the same number of cycles. Comparing both on a fixed millisecond scale can hide important low-frequency behavior. The periodical CSD addresses this by expressing decay in periods, or cycles, instead of using one fixed time scale for the entire frequency range. A resonance can be represented as a sine wave whose amplitude falls exponentially with time. The decay constant depends on resonant frequency and Q. The period of the sine wave is the inverse of its frequency. When time is rewritten as an integer number of periods, the frequency term drops out of the decay expression. What remains depends on Q and the number of completed cycles. This means that resonances with the same Q produce the same decay shape when the horizontal scale is measured in periods, even when their frequencies are very different. The periodical CSD in this example was produced with a sequence of pulsed sine waves. It reveals distinct ridges below 1 kHz and a delayed resonance near 3 kHz. Because the time scale varies with frequency, a 500 Hz resonance lasting 15 periods represents about 30 milliseconds. At 3 kHz, 37 periods represent only about 12 milliseconds. This cycle-based view improves low-frequency resolution and can reveal resonances that are difficult to see in the ordinary CSD. Periodical CSD offers two useful advantages. Pulsed sine waves provide strong excitation, and the period-based scale improves low-frequency detail. But the technique also has limits. The longer effective time span at low frequencies makes the result more vulnerable to reflections in a reverberant room, and if the sequence contains too few test frequencies, it may miss a narrow resonance between them. Ordinary CSD and periodical CSD are therefore complementary tools. Each reveals behavior that the other may not show clearly. Not every peak or dip is caused by a driver resonance. Cabinet edges, raised driver frames, and grills can diffract sound. Here, adding the grill produces deep response dips near 3, 5, and 14 kHz, together with a broader peak near 12 kHz. The grill frame creates an abrupt change in the baffle surface. When the wavefront reaches that edge, it generates a secondary wave that interferes with the direct sound from the tweeter. The direct and diffracted waves travel different distances before reaching the microphone. Their relative phase therefore changes with frequency. At some frequencies they reinforce each other, and at others they cancel. The result is a comb-like pattern of peaks and dips. Because this grill frame is only 7 mm thick, it has little effect below about 3 kHz. At shorter wavelengths, however, the interference becomes severe enough to reshape the measured response. Off-axis measurement helps us distinguish diffraction from resonance. A driver resonance is inherent in the moving system, so it tends to remain visible as the microphone moves to different angles. Diffraction depends on geometry and path length, so its peaks and dips change with angle. In this graph, the severe grill-on dips seen directly on axis are greatly reduced at 30 degrees off-axis and are replaced by smaller variations at different frequencies. That change confirms that the original disturbance came from diffraction rather than a persistent driver resonance. Cepstral analysis provides another way to examine reflections and diffraction. In simplified terms, it converts repeated or delayed structure in the frequency response into features on a time-like axis. The inside edge of this grill is about 5.5 centimeters from the tweeter axis, so its diffracted wave arrives roughly 160 microseconds behind the direct sound. The cepstrum shows a feature at that delay. A second feature near 210 microseconds corresponds to the outside edge. The earliest spikes must be treated carefully, because they can belong to the original impulse rather than a separate reflection. Frequency response shows the loudspeaker's tonal balance. Cumulative spectral decay reveals stored energy and resonances over time. Periodical CST makes decay easier to compare across frequency. Off-axis response and cepstral analysis help separate diffraction from resonance. None of these measurements tells the complete story on its own. Their real value appears when we compare them, understand their limitations, and connect the results with careful listening. Objective measurements and subjective experience are not competitors. They are two views of the same loudspeaker.